Okay, so this is our second video on double integrals over general regions. What we're going to do here is we're going to look at what we're going to call a type 2 problem. And the graph of a type 2 problem looks like this. We're actually going to be bound over two y values, c and d. And we're going to create two functions here that are going to be functions with respect to y. So we'll call this one like x is, h sub 1 of y, and this one here will be x is h sub 2 of y. And kind of what plays out here is that if this is the D region, then the double integral over d of f of x y dA should be the iterated integral from c to d. But now we're going to put these two functions on the inside, h of y, h2 of y of f of x y. And then we have to do the d, this time we have to do the dx first, and then the dy. Okay, so sorry about the sloppiness. Maybe we can clean that up a bit. It's kind of hard to read. So this is h1 of y, h2 of y, f of x, y, dx, dy. All right, awesome. So we're going to work an example, and we're actually going to look at the same, the exact same problem that we did as a type 1 problem, but we're going to reformat it as a type 2 problem. Okay, so if you recall from the last video, we had this type 1 problem, okay, where in the type 1 setting, the domain was listed as the set of all x, y, where x is strictly between 0 and 2, and y is stuck between x squared and 2x, okay? And we had the f of x, y being x squared plus y squared. And if you actually go back to the last video, you'll see that this came out to be 216 over 35, okay? So remember that number. Okay, so if I think about this, this is like x squared is a parabola, right? So that's going up, right? And then the line to x equals 2y starts at the origin and kind of, yeah, that's ugly. It starts at the origin and then crosses through this parabola, right? So there's the line, and this is the D region that we're talking about. So this went from 0 to 2, and it has the x squared on the bottom, and it has the 2x on top. But you can visualize the same problem in a completely different way. You could see this starting at y equals 0. And let's see, since this is x squared and 2x, right? So 2 squared is 4, 2x, 2 times 2 is 4. So this is going to go from 0 to 4, right? Let's see, this is the line y equals 2x, which means it's the line x equals 1/2 y, right? So this line is x equals y over 2, right? And this curve here is y equals x squared. So in the first quadrant, this is going to be x equals the square root of y. So this curve is the square root of y. So D could actually be written as the set of all x, y, such that, well, let's see, x is going between, so at a given slice, x is going to be between y over 2 and the square root of y. and y is going to be between 0 and 4. So now we've put the constants with the y and the functions with the x. So in theory, if I use this as my d and I iterate over the x and then the y, I should end up with the exact same numbers. So instead of visualizing this as up and down, I'm visualizing it as left and right. Okay, so we should be able to make an iterated integral here, right? Where we have x squared plus y squared, but we're going to iterate the x first and then the y. Y is running from 0 to 4. X is running from y over 2 to the square root of y, right? So if I take the antiderivative, I'm going to get a third x cubed plus xy squared from y equals over 2 to square root of y dy, right? Okay, so let's make our substitutions. All right, so in the front we're going to use this square root, so this is 1/3 x to the 3 halves, or y now to the 3 halves. Y to the 3 halves, there we go. Plus, let's see, square root of y times 2 is y to the 5 halves minus, and then this is going to give me, let's see, y over 2 cubed. 2 cubed is 8 times 3 is y cubed over 24, I think, right? And then, let's see, plus, let's see, this is going to be y cubed over 2. And this is all still dy. All right. So I now have the integral from 0 to 4, 0 to 4, right? I think that's still going to give me a third y to the 3 halves plus y to the 5 halves. Let's see. This is like 13 over 24 because it's 1 and 12. Yeah, 13 over 24 y cubed dy, right? Okay, so it's time to anti-differentiate again. So let's see. 3 halves is going to go to 5 halves, so that's right. 3 halves over 5 halves, that's going to give me 2 over 15 y to the 5 halves. 7 halves is going to be 2 sevenths, right? Y to the 7 halves minus 4, right? So this is going to be 13 over 96 y to the 4th from 0 to 4. All right, so we got to substitute the 4 in for all of these because the 0 is going to make it all 0. Okay, so I'm substituting in the 4s. I have 2 over 15, and let's see, 4 square root of 4 is 2 to the 5th is 32, right? Plus 2 sevenths. This 2 to the 7th is going to be 128 minus 13 over 96, which is 4 to the 4th power, which is 256. Okay, so this is the same as 64 over 15. This is going to be 256 over 7. And this is going to be minus 3,328 over 96. All right, combining those, I'm going to ask you to trust me a little bit here, but this comes out to be 216 over 35, which is exactly what we expected to happen. And it is exactly the same value that we got when we did it as a type 1 problem. All right, so type 2 is a lot like type 1, except for you're going sideways instead of up and down. And there you go.